Okay, we're on the last section of chapter 17, energy and change of phase. Let's dismiss there. And energy and change of phase. Uh, from a solid to a liquid to a gas phase, you have to add energy. If you're going to go from gas to liquid to a solid phase, you have to remove energy, and that's what this little graphic here shows. Uh, if you follow the arrows from a solid to a liquid to a gas, you have to uh, put in energy. The solid has to absorb energy, the liquid has to absorb energy, and so forth. To go in the opposite direction, gas, liquid to solid, energy is released. You need to remove slow down the kinetic energy. So energy is released. Um, some examples, um, the cooling cycle of refrigerator pumps, a special fluid that vaporizes and draws heat from the stored food. The gas that forms along with its energy is directed to the condensation coils outside the refrigerator where heat is released and the fluid condenses back to a liquid. You feel the condenser coils. You put your hand, a lot of times in the back of your refrigerator, you'll feel the heat from the uh, the coils. It's taking heat from the refrigerator and throwing it to the outside. Air conditioner pumps heat energy from one part of the unit to another. Um, it pumps the heat energy from one part to another. The heat of fusion, the amount of energy needed to change any substance from solid to liquid and vice versa. That's the heat of fusion. Sometimes it's called I think in your book, it's called the latent heat of fusion. Um, Examples, the heat of fusion for water is 335 joules per gram. Uh, Farmers in cold climates replace frozen tubs of water with unfrozen ones in their cellars to prevent jars of food from freezing. Because of the high water content, the water will take a lot of the energy. Um, Heat of vaporization, uh, the amount of energy needed to change any substance from liquid to gas and vice versa, uh, sometimes called the latent heat of vaporization. The heat of vaporization for water is 2,260 joules per gram. Uh, in in briefly touching a hot skillet, energy that normally would flow into your finger instead vaporizes the water. Hence, you're not burned. That's talking about if you dip your finger in water and touch the hot skillet. Not necessarily recommended, but it's just giving you an example. Okay, here's a graph showing the energy involved in heating and the changes of phase of 1 gram of water uh, from a from a piece of ice, not only a piece of ice, but a piece of ice at minus 50 degrees C. You can see the minus 50 here. So now um, when we talked about specific heats, it was either calories per gram per degree C or joules per gram per degree C. In in the latent heat of fusion and the latent heat of vaporization, it's just joules per gram because you're not changing. I mean, you're not. You're just putting energy into the system. Uh, you're not really raising the temperature. We'll see that as we go through the calculations. Now, there's going to be a lot of calculations here. Don't on homework and quizzes. I don't think I've asked much for calculations. This is just for demonstration and explanation purposes. So let's look at this first part. Now it's not listed here, but I did calculate it. The specific heat device is 0.502 calories per gram or 2.09 joules per gram per degree centigrade. Um, I didn't say the degree centigrade. Now here you can see we are raising the temperature, so there is a degree C. To raise 1 gram of ice from minus 50 degrees to zero takes 1 gram times 0.502 calories per gram per degree C times 50 degrees C equals 25 calories. Or the alternate is 1 gram times 2.09 joules per gram per degree C times 50 degrees equals 105 joules. So it takes 105 joules to warm ice at minus 50 uh, up to 0 degrees, where it can, at that point, start melting. So just raising its temperature, this is specific heat of ice. Now, the latent heat of fusion for water is 80 calories per gram or 335 joules per gram. Notice there's no degree C here because it's flat. You can see it's flat. It has not changed uh, temperature. So to melt 1 gram of ice takes so 1 gram times 80 calories per gram gives you 80 calories or 335 joules. Okay, now the specific heat of water is 1 calorie per gram per degree C or 4.19 joules per gram per degree C. So to raise 1 gram of water from 0 degrees C to 100 degrees C takes 1 gram times 1 calorie per gram per degree C times 100 degrees C equals 100 calories, or in the joule equivalent is 419 joules. You can see they have both the calories and the joules listed on this graph. And finally, we're going to get to vaporization. Again, all we're doing is we're putting in energy. We're not raising the temperature. It's still at 100. The latent heat of vaporization for water is 540 calories per gram or 2,260 joules per gram. So to vaporize 1 gram of water takes 540 calories or 2,260 joules. So if we look from when we were at minus 50 degrees, we had to put in 745 calories of energy or 3,119 joules of energy to go from minus 50 degree temperature ice to steam. Now I didn't do it for steam. There is a specific heat for steam, but they don't show what the final temperature is, so we're not going to do that part of it. Okay, when snow forms in clouds, the surrounding air is cooled, warmed, insulated, or thermally conducting. Well, it's warmed. The change of phase from a gas to a solid, which releases energy. Okay, which involves the greatest number of calories. Condensing 1 gram of 100 degree steam to 100 degrees water, cooling 1 gram of 100 degrees C water to 1 gram of 0 degrees ice, or cooling 1 gram of 0 degrees C ice to near absolute zero. Remember, that's a change of minus 273 Celsius. Well, it's actually A, condensing 1 gram of 100 degrees Celsius steam to 100 degrees water. And here's the explanation. Condensing 1 gram of steam releases 540 calories. Freezing 1 gram of water releases 80 calories. And cooling 1 gram of ice from 0 to minus 273 releases 136 calories because the specific heat of ice is 0.5 calories per gram per degree C. Thus, condensing a given amount of water involves more energy than melting to a smaller mass of water or cooling a similar mass of ice. Ice is put in a picnic cooler. To speed up the cooling of the cans of a beverage, what is important? It is important that the ice A melts, is prevented from melting, or be in large chunks. And the answer is it melting. For each gram of ice that melts, 540 calories is taken from the beverage, whereas for each degree that ice warms, only zero point 0.5 calories are taken from the beverage. And that's the end of the chapter.